Hi everyone, today we'll be solving yet another GFG PoTD, which is brothers from different roots, and this is easy level problem. So you will be given two binary search trees rooted at n1 and n2, and you are also given a value x. You want to find all the pairs a comma b such that a plus b equals to x, and a belongs to one binary search tree and b belongs to another binary search tree. So if you have solved two-sum problem from lead code, you are pretty much aware of the solution because it is just two-sum problem, but instead of being in the same array, these values are from two distinct binary search trees. So we can do a easy DFS or BFS to find the values, right? So what is the logic for this two-sum problem? Let's discuss that first. So let's say you want to find two values a and b such that they sum up to x, right? So how do you find this? So the logic for this, the optimized O of n approach is that what you do is you do a equals to x minus b, right? So whenever you encounter such a in the first array such that this value exists, right? In like you pre-compute from the second array, like you iterate in the second array, you store in the map x minus b values for all the values in the second array, and then you iterate in the first array. So when you iterate in the first array and you encounter values such that this is equal to this, so means you have found a pair such that this value holds, right? So then you increment your answer, so you do a answer plus equal to 1, right? And that's what's exactly we are going to do in this problem. But instead of iterating or traversing normally, we are going to do a DFS or a BFS. Good. So the prerequisites for this is DFS, BFS and the two-sum problem, and not just the two-sum problem but the O of n approach of two-sum problem, right? So let's just jump right into the code, because if you know these things then it is pretty simple to solve. So here I have done a BFS approach. So here I have taken a map. So you can also use an order map for better complexity, but it doesn't matter too much. Then I have taken a queue. So in BFS we use queue. I just push root, which is the first root node. Then I do a simple BFS traversal while not queue is not empty. So I take the size. So this is like the level order traversal for BFS. While size minus minus, I take out the root. Then I increment its value, which is x minus the root value, which I just told you, x minus b. I increment the value, and then if there are left and right nodes of that current node, then we push them into the queue as well. Then I take an answer and I do the same for root 2, and while queue is not empty, so we are just doing the BFS traversal, right? We are popping the node out, and if we find that node of data is there, like a is there, so we have to increment our answer by 1. Then again the same procedure if it has a left child and right child, so we do that, and then we return the answer, right? So the complexity of this code is O of n time and O of n space, because O of n we are doing BFS, right? And space complexity for our queue, which will be like in the case of okay, let's just not go into that. So yeah, that was pretty much for this video. Thanks for watching.